In week 1, we looked at the consequences of different ways of sharing energy among a system or ensemble of particles with quantized energy levels or states epsilon I, that is, atoms or molecules. This gave us a new perspective on temperature, which we'll come back to in week 2, and also introduced 3 new important quantities. These are the Boltzmann distribution, the molecular partition function, and the characteristic temperature. The characteristic temperature, theta, is defined as the energy difference between the ground state and the first excited state, but expressed in units of temperature. This is simply calculated by dividing the energy difference in joules by Boltzmann's constant in joules per Kelvin. The characteristic temperature is a property of a set of energy levels of an atom or molecule. It's not temperature, but it's a property that has the same units and can be compared with a temperature. The definition comes from the Boltzmann distribution applied to the first excited state. If we substitute the characteristic temperature definition, we get a simpler looking expression for the relative population of the first excited state. When the temperature of the system equals the characteristic temperature of a set of energy levels, this is a kind of tipping point. We use it to decide whether the first excited state is significantly occupied at a particular temperature. So, if T is far above the characteristic temperature, then theta over T is very small, even approaching 0, and e to the 0 is 1. The Boltzmann equation then says that there are almost as many molecules in the first excited state as there are in the ground state. Conversely, if the temperature of the system is well below the characteristic temperature, then theta over T is very large, and e to the negative of a large number is almost 0. There are then only a small proportion of molecules in the first excited state compared to the number in the ground state. As an example, consider a system whose characteristic temperature is 150 Kelvin. We can use this characteristic temperature to get information about the occupation of excited energy levels if the system is at room temperature, 298 K. The ratio of occupation numbers of the ground and first excited states, N1 star over N0 star, calculated using the Boltzmann distribution, is 0.604. Put another way, if the ground state occupation number was 4,000, then there would be 4,000 times 0.604 equals 2,416 molecules in their first excited state. We'd call that excited state significantly occupied. If we look at the same system at a much lower temperature, like 40 Kelvin, then N1 star over N0 star is 0.023. That is, for every 4,000 molecules in the ground state, now there are only 94 in the first excited state. It's not significantly populated. We might also reasonably expect that there would be few, if any, molecules in any of the higher energy states. Finally, if we look at the system at a much higher temperature, like 2000 Kelvin, then N1 star over N0 star is 0.928. That is, the ratio of molecules in the ground and first excited states is almost 1. That's definitely significantly populated. Again, we might expect that higher energy levels would also be significantly populated, as long as the energy levels were more or less evenly spaced. This is what we mean by comparing the temperature of a system with the characteristic temperature of a set of energy levels of a molecule to decide whether the excited states of that molecule are thermally accessible at that temperature. Now the molecular partition function, sometimes called the sum over states. This is a weighted sum of occupation numbers, or of occupation probabilities, of all the energy levels, always relative to the lowest energy level or ground state. This can be expressed in summation notation using occupation numbers, occupation probabilities, or Boltzmann factors. Boltzmann factors are what we call the exponentials of the energy differences divided by Kb times the absolute temperature. The partition function is itself a number and has no units. Roughly speaking, the partition function gives us an indication of the number of occupied states at a particular temperature. The partition function includes the ground state occupation in the first term of the sum, so it's never smaller than 1 at low temperature, but can increase to be a very, very large number at higher temperatures. Suppose we examine a system of 10,000 molecules, which is a small system from a chemical perspective, but already large enough for us to apply the law of large numbers and only have to consider the most probable distribution or Boltzmann distribution to describe it. Now suppose that we can measure that 4,000 of these molecules are in the ground state. What is the partition function? The number of molecules in the ground state, N0 star, is 4,000. So the partition function is N over N0 star, or 2.5. Equivalently, the probability that a molecule in the ground state is 0.4, so the partition function is 1 over 0.4, or 2.5. Again, only a few energy levels are occupied. 40% of the molecules are in the ground state, of course, and the rest are distributed into a few of the lowest energy excited states. Note that the partition function does not have to be an integer. And we don't need to know the details of the energy levels or the temperature to determine Q by this method. If we did know T, then the Boltzmann factors would be used to calculate individual occupation numbers of excited energy levels at a particular temperature. Now, on the other hand, if only 200 molecules were in the ground state, then the partition function would be 10,000 over 200, or 50. This would mean that many excited states were occupied and that some molecules were in very high energy states. And if all 10,000 molecules were in the ground state, which means none are in any of the excited states, then the partition function would of course be 1. Now, the partition function is a central tool in statistical or molecular thermodynamics, as it provides the pathway from quantum mechanical properties of individual atoms and molecules to the observable properties of macroscopic systems or ensembles of molecules. Here's an example. If we know the energy of each molecule, epsilon I, and the number of molecules with that energy, Ni, then we can calculate the total energy of the system by summing the product of Ni epsilon I. If that system is in its most probable configuration, that is to say it's at equilibrium, then those Ni's are all Ni stars in our notation and can be calculated using the Boltzmann distribution. So now, with a little bit of algebra and calculus, which is not examinable in this unit, but we're showing you so you can check it if you want to, we can get an expression for the energy of the system of molecules as a derivative of a partition function. This final expression relates energy and temperature, two macroscopic properties of chemical systems, without referring back to the individual molecules' energy levels. We won't be taking derivatives of general summation expressions, but of specific formulae that we determined this week. Once we have the internal energy, then we can calculate other things like pressure or enthalpy or heat capacity. We'll come back to this later. Our trajectory over the next few lectures will be to determine the characteristic temperature and the partition function for different types of energy levels associated with different types of molecular motions or degrees of freedom. Along the way, we'll illustrate how the partition function can be used to calculate the internal energy and or heat capacity of a system of molecules, and fill this table in with usable formulae. You'll see this slide often in lectures as the table gets completed. The completed table will also be provided with the exam, and later we will also use partition functions to calculate equilibrium constants for chemical reactions.